Before we talk about solutions, we should probably define some words we're going to be using. Solute is what is dissolved in the solution. Typically, we think of this as a solid, but it could also be a gas, like carbon dioxide and pop, and it could also be a liquid, like ethanol in beer. The solvent is the liquid portion. It's the majority of your solution, and a lot of times it is water. Doesn't have to be, but it is a lot of the time. The solution is your solute and solvent together. A precipitate happens if some of the solute is solid, and this can happen if you have too much solute to dissolve in the solution, or if the solid isn't capable of dissolving. Remember, in Table F we have exceptions to dissolving. So this is a solid in a solution. All right, a couple other definitions. An unsaturated solution can actually dissolve more solute, so they don't have the maximum amount. They can still have more dissolved in it. A saturated solution has the most solute possible at that temperature and that amount of the solution. So this is the most solute possible. We're going to be looking at a new graph today from our reference tables, Table G. In Table G, you're seeing the solubility curves for different substances. The curve, the line itself, represents saturated at all of those temperatures. This graph is based on 100 grams of water, which just happens to also be 100 milliliters of water. So at each temperature, you can see the amount of the solute that you would need in order to have saturated solutions. So if you have a point below the line, it's unsaturated. On the line is saturated. And above the line, you could have two situations. If you had a substance where the solution was heated up, and therefore you could add more solute and it cooled down, sometimes the extra solute that couldn't dissolve stays in solution for a while. That's a situation we call supersaturated. The other situation is where you actually have some of the solute coming out of solution as a precipitate. So this X above the line could be supersaturated if it managed to stay in solution, or it could be saturated with some precipitate falling out of the solution. And the amount of that precipitate would just be the difference between where that point is and the curve of saturation. So we've mentioned that temperature can affect the solubility of a substance, so let's record some of that information. If something is a solid, increasing the temperature will increase the solubility. Think of maybe Grandma makes candy. She always heats up the water so she can dissolve more sugar in that solution, sugar being the solute, water being the solvent. So for solids, this increases the solubility. For gases, the situation is different. Gases, the molecules are very, very far apart, and in order to dissolve in a liquid, they need to be closer together, like liquid particles. So for solids, it increases, but for gases, it actually decreases the solubility to have an increase in temperature. Conversely, when we decrease the temperature, for solids, the solubility is going to go down, but for gases, it's going to go up. Think about pop or soda, depending on where your family's from. Pop, we like to have it really cold, and we also like to have the top sealed very frequently instead of opening it over and over again. In order to keep the carbon dioxide dissolved in the pop, you need to keep the temperature cold And then you also need to keep the pressure high. In fact, inside a bottle of pop, the pressure is 4 atmospheres. That's 4 times normal pressure in order to keep those molecules close enough to each other to stay dissolved in the liquid. So for pressure, with an increase in pressure, it actually increases the solubility of a gas. However, there is no effect on solids. All right, we're going to start using Table G in order to answer some questions about the solubility of different substances. So I'm going to bring in Table G. And for this first question, all we're going to do is we're going to read the graph. So we have KNO3 we're looking for. There's a lot of curves there, so you need to make sure you're finding the right one. And 100 grams of water, which is good because that's what our graph is based on, 100 grams of water at 60 degrees Celsius. So we're going to find 60 along our x-axis, follow it up to the curve for KNO3, which is right about here, and then follow it over. The interval on this graph is the same, 10 for the x and 10 for the y. So when we follow this up and over, we're getting about, 108 grams of KNO3 that'll dissolve in 100 grams of water at 60 degrees Celsius. Now, sometimes they do it based on a different amount of water. So we're going to do this again, but we're going to do this at a different temperature for the same substance. So 40 degrees KNO3, follow it up and over. I'd say that's about 64 grams. It's 64 grams in 100 grams of water. We want to know what it is in 25 grams, so I'm setting up a proportion here in order to solve this. You might have been able to do that in your head, knowing it'd be a quarter of what you would normally expect it to be, but it's best to set up the proportion because sometimes the math isn't going to be as easy. To solve, I'm sure you'll want to cross multiply. One thing I'm going to show you right now, and you don't necessarily have to do it this way, you can do all the contortions to get x alone. When you cross multiply, you don't have to cross multiply on both sides. You can just cross this, and then you won't have to solve for x. X is already solved for. So we're going to do 64 times 25 divided by 100. And when you do, you will get 16 grams. Next couple of questions are asking us which substances are solids and which ones are gases. If you recall, we said that solid solubility increases with increased temperature. So any curve that's going uphill is going to be a solid. So we can start listing some of those. Ki is a solid, NaNO3 is a solid, KNO3 is a solid, and we could go on. Which substances are gases? Well, we said that gases' solubility actually decrease with an increase in temperature because they like it cold. So we have HCl, NH3, and also SO2. So all these times you've been using hydrochloric acid and ammonia in lab, they're actually gases that are dissolved in those substances. That's why you'll often notice that there is a stopper on those stock solutions because otherwise they evaporate over time. All right, next question. Which substance is most soluble at 10 degrees? So at 10 degrees, which of these can hold the most of our solute? So heading up 10, it will be Ki. So we can dissolve the most Ki in water at 10 degrees. And then the next question, which one's least soluble at 60? So the one that can dissolve the least would be SO2. And then the last question, if a solution contains 50 grams of HCl and 100 grams of water, so we're not going to have to convert or set up the proportion like we did in number 2, at 50 degrees, how much more HCl can be added to saturate the solution? Okay, so they're saying that they've already put 50 grams and 100 grams of water at 50 degrees. So let's see where that point is. So we have 50 degrees, and they've added 50 grams. So that point is going to be right here-ish. There we go. So they want to know how much more we could add. Well, saturated for HCl at 50 degrees is actually right here. That means saturated is typically about 58. So 58 would be saturated. We've already added 50, so we have 8 grams we could still add to saturate the solution.